Hey, good morning, everybody. So today is the dynamic models class. I think this is not going to be a very long class because there's nothing new in this class. At least no new concepts, right? If you read the class, you see that we can treat dynamic models in the same way what we've done before. Of course, I'll do a bit of a summary, and then we'll have a break, and after the break, I hope we're going to be done in the first hour, right? And then after the break, Wouter will, for the volunteers, discuss like sort of all the or kind of internships and projects that we have available in our group, not just in our group but also in companies, and perhaps in the future, if you want to do a project in another group, also fine. But if you want to, let's say, do a project in another group, in another company, and still think I want to do a Bayesian approach, then you can also, of course, ask if one or somebody in our group wants to become like a second supervisor or join the project or something. So Wouter will talk about the kind of projects that are available. So one thing we did over the break is we moved the location of the repository of RxInfer. If you would still have the old, RxInfer, our toolbox, was in GitHub under the Bias Lab, our research lab organization, and we moved it to its own organization. So if you want to access anything in RxInfer and you go through Google search may still point you to the old location. The best thing is to just go to rxinfer.ml, then press the documentation or examples or whatever, and I think Google search will also at some point update the links. So let's talk about dynamic models. What's a dynamic model? Well, a dynamic model there's some temporal dynamics, right? Let's say we have observations x1, x2, x3, x4, and we have a probability distribution over the observations, but the order matters now, right? So x1 comes before x2, x2 comes before x3, and x3 comes before x4, and in this case, that would be a different data set than if the sequence will be x2, x1, x4, x3, right? So the order matters now. Well, then if the order matters in general, let's say speech signals or video signals or whatever, biomedical signals, we generally make models where where a particular observation depends on something in the past. Right? If I speak and have a microphone, I observe a speech signal. Yeah, that what I observe, you can't really say that if I sample 16,000 times or say 44,000 times per second the speech signal, you can't really say that this sample is completely independent of this sample. There is some slowness in how fast I can move my tongue and my throat and vocal folds. So there is going to be some relationship. X2 can only move a little bit from x1. So knowing x1 will tell you something about x2, and knowing x2 will tell you something about x3. And maybe in order to predict x3, it helps to know both x1 and x2. Right. So what we will not do is we will not write this model x1, x2. x3, x4, we will not assume, oh, that's just it's just the probability distribution for the individual observations and then multiply them. We cannot assume that now because the order matters and xk in some way depends on the past. We can always write this as px4 given the past times the past. Right? This is always true. And this I can always write as px3 given the past times, this is always true. And this I can always write as this. So that's just the product rule. I haven't done anything yet. It's just the product rule. So I can always write this as basically pxk given its past, px1, x2 to xk minus 1. K is 1 to, where do you want k to be? Let's say 4 in this case, right? 4. Boom. This is always true. And so this looks now different from this, right? Here we assumed, xk, I don't need any past to predict xk. Here we say, the past may help. I didn't really use anything yet than the product rule. So what we need to do now is to choose models for this. And generally what we do, as you can see, if time keeps running, if I have streaming data, k will get higher and higher and higher, 4, 5, 6, 7, 8, and so forth. And the past will just grow, right? So at some point we need to cut it off. And what we will generally do then is models of this nature. You say, hey, xk is going to be dependent on, xk minus 1, xk minus 2 until xk minus, let's say, m. So m samples from the past. That's a model assumption where we just basically say, well, when the past gets really deep, we ignore it. Yes?
In the formula, you wrote the multiplication of p of xk, x1, x2, xk minus 1, right? Along with that, should we also write p of x1, x2, xk minus 1?
Sorry, can you say the question again?
So in your example with x1, x2, x3, x4, you wrote p of x4 given x3, x2, x1. So
Yes.
p of x3, x2, x1.
Yes.
Shouldn't that second term be included in the general formula?
So the question is, shouldn't this second term
Be in the general formula.
be put here? Okay. So why don't I see this term here? Because basically what I tried to derive here is that this expression is this times this, but this is this. So times this, times this. So this expression is this guy times this guy times this guy times this guy, which I write down here, right? And so that's the most general model you can think of. I haven't done any strange assumption yet. I've just used the product rule. So this is completely general, even if it wasn't an ordered. This is just always the case, right? But by writing it in this way, you're writing it in factors, where you can say, okay, the current sample depends on the past, and it's very useful for sequences where the order matters, right? So I haven't made any assumption yet, other than rewriting this model into each that's completely equivalent, But now I have factorized it into probability distributions over the current sample given the past. This would grow, right? Grow. So what we usually do, and now we make a model assumption, is we say, now let's just keep the previous capital M samples. And this is called an autoregressive model. You do regression for xk based on itself, hence autoregression. Right, so, or shortly an AR model. And so AR models or autoregressive models are very common everywhere in modeling literature, but for time series, like for economic time series, for biomedical time series. Autoregressive models are probably one of the first things you want to look at or try. And here is an autoregressive model of, in this case, of kth order, right? We say, okay, so the probability for x of t is a linear function of capital K samples. That may not be a perfect model. These capital K samples may not perfectly predict x of k, so we leave room for some uncertainty, Gaussian noise with uncertainty sigma. That's another regressive model. And so in control theory, you see these models, but you see them everywhere in time series analysis, also in, like I said, in economics and biomedical analysis. So what's nice about this is now it's in a form that, for us it's just a probability distribution, and we can start working with it in any way. That's what we've learned. We can do some rules and product rules because that's the only thing we need to do, right? So we can learn parameters A of k if you want. You can learn sigma k from observations. You can we call that system identification. It's whatever you want to do. Now, there's nothing wrong with this model. It's just that, it says here x of t depends on the past observations. So your speech signal depends. Let's say you have a speech signal. It depends on past observations of speech. Well, really, what it really depends on is the location of your vocal folds, of your tongue, of your mouth, right? So it's not directly dependent on the previous observations. It's directly dependent on hidden causes. So there is another class of models, an extension of these autoregressive models that we call state space models, where we say, we have an autoregressive model for state transitions, and these z of t may be multidimensional. Maybe z of t are like the location of your vocal folds and the location of your tongue and the speed of your tongue and all kinds of parameters of the physical system. And we're going to say x of t, depends on the state of that system, right? Of your physical system. So you now have an autoregressive model for what we call these hidden variables. We call them states. If they also change over time, it's just a label for hidden variables. We also have hidden variables called parameters. Why are they called parameters? Well, that means that we assume that they don't change over time, but if they are allowed to change over time, we call them states. But in both cases, from a Bayesian perspective, they're just latent variables. They're just variables in our system that are not observed. And if we want to know what these values are, we have to do inference over these values, given our observations. There's nothing to it. Right? So this model is called a state space model. And a state space model, we have to make choices now for I mean, we have to start it off, of course, but more relevant, how do observations depend on hidden states, and how do these hidden states move in time? I cannot, if I have my tongue folded up in a certain way, I cannot have, let's say, in a millisecond later, my tongue folded up the other way. It's like a continuous process. So the hidden states are very well modeled, usually by an autoregressive model, and it's also very natural to just say, well, what you actually hear, your speech signal, depends on the state of your physical system. Yes?
In a Gaussian mixture model, why do we call the hidden variables also states there?
In a Gaussian mixture model, why do we call the hidden variables Z? Okay, so generally speaking, if in a system you have, let's say, in a system, I just say there are two parameters. It's just a system of variables, and we generally can categorize them into variables that we observe. Let's call them X, and variables that we do not observe, Z. And then, generally speaking, the variables that we do not observe, we can categorize them in stuff that doesn't change and stuff that, let's say, that is a function of the observation. These we call states, these we call parameters. So here, the Z of t are a function of the observation, so we call them generally states. Now, this already looks like a complex model, right? But if we draw the factor graph, and we can draw the factor graph here, then you kind of can see what sort of happens, right? I have a model here with hidden states Z, and so here I have Z1, and this is also Z1, and this is also C1, because there's a equality node. And we say X1, my observation depends on Z1, and then once I make an observation, I make a transition, your autoregression, to Z2, and that can generate an observation, X2, and so forth, right? You have transition models, and you have emission models or output models, observation models, but whatever you want to call them. This is a state space model. And you just tell me now, what do you want to do in that state space model? There's three things that we usually want to do. We want to do filtering, smoothing, or prediction. I mean, there's other things you can do, but that's usually what you want to do. If you want to do filtering, we say filtering means basically to determine this. The probability for the hidden state given everything we've seen in the past. Right, so what is the probability distribution over the location of my tongue and the location of my vocal folds and so forth, given the speech signal that we've seen from 0 times? So how do I do that in a vector graph? Well, I want to know the probability distribution for this variable. This is Z of t, and I want to incorporate all these observations. So what I'm going to do is I pull that graph from here, pull it up, and I see sort of like two branches of the tree. This is a branch and this is a branch, and then I just pass messages from the bottom to basically the edge where I pull up the graph. So this one, 3, 4, 5, 6, 7, 8, and so forth. This one, and here from the other branch, here you multiply, right? And then you get your posterior for ZT, taking into account all the observations in the past. Right? So now that procedure is called Kalman filtering. And later in the let's say, going from here to here, namely going from P of Z2 given, no, let's say going from here to P of Z2, I want actually from here, P of probability for Z2 given all the past to the probability for C3 given all the past means you have to go through a transition and you have to pass the message here and you have to multiply here. Right? Now you can also do that manually here. Right? You can just compute. You can compute. Okay. I want to compute P of ZT given the past. X super T is just a notation that I introduce here. X super T is just a notation for X1 to T. Right? So this thing, right, you equal, or that thing times the evidence, equal, and then I continue. So here it is expressed in terms of basically the prior there, z of t minus 1 given the past at at x of t minus at t minus 1. And then when I fill in Gaussians, I get an answer here. This is the Kalman filter. Who in this classroom has done a class in control theory and has derived a Kalman filter in that class? Nobody has derived a Kalman filter in control theory? Okay. So the Kalman filter is very often derived. Well, look in your control book. It probably has been derived, or maybe not in your class. But Kalman filtering is also very common in control theory, because, well, you have a system. You need to control the system. You want to estimate what's the state of that system, right? And that state is represented by z of t. You can't use future because you haven't observed the future, so you want to filter. So Kalman filtering was even used in the 1960s to basically to go to the moon. Kalman filters are very used for that because you have to control that rocket that actually goes to the moon and not to some other place, right? Generally, Kalman filters are derived. It takes like 10 pages, and then you don't even get the evidence, because in most derivations, just go to Wikipedia and do a derivation of a Kalman filter. You'll see that you see a whole long derivation, not recognizing that it's just Bayesian inference. And you'll get exactly these equations without having the evidence. And this derivation, well, this is like 6-7 steps, but it's just some product rules in these 6-7 steps. There's nothing to it. Of course, I'm not going to ask this derivation on an exam, because you'll probably make some mistake, as I would, right? The point is, it's not that it is straightforward to derive a Kalman filter. It's just, you just get lost in the in the variables. the best way to do a Kalman filter is to just make a toolbox, a vector graph toolbox, and pass messages. Right? That just divides it up, the whole problem of Kalman filtering in small operations, small messages. So you need to pass, I don't know, like 1, 2, 3, 4, 5 messages to go from time step to time step, and these 5 messages will then actually implement this Kalman filter, right? That's much easier to see than this. But it's the same thing. Now, sometimes you want to do something else with your state-space model. You want to do prediction. You want to say, I have received observations until x of t, but then now I want to make a prediction for x of t plus 1 given the past x until t. I have not observed this one. This is actually what I want to predict. So I need to compute now this message, and it goes the same way, right? You go the same way, you filter, so up till here you've done filtering, and then you just run forward, right? You say, oh, okay, I pass here, I pass here. This is a message which says, this is what this graph thinks about this variable. Well, what does this graph think about this variable? Well, your model, and it also taken into account these observations. That's what this is. It's just you just need to compute this message. The nice thing about doing it in a vector graph is, or if you have a toolbox for it, you don't have to do now a new derivation of your Kalman filtering, right? But now Kalman prediction. And sometimes you want to do something like smoothing. You want to compute, what is my belief in ZT, not only after having observed everything here, but what if I actually can observe samples in the future? You do that a lot for machine learning, when you say, okay, I just have a whole database, and I want to compute the posterior for a particular variable, a parameter, given a whole database, right? In your vector graph, well, you pull up your vector graph at this edge. You have 2 branches in your tree, left and right. And so from the left tree, you pass the messages, the red messages, to the forward message for Z2. Here you also have observations, okay? You've just passed the messages in the right branch, the green messages. You get a backward message, and you multiply and normalize, and you have your posterior. And that's smoothing. So whether you want to do filtering or smoothing or prediction, you just build the graph and you draw the messages. If you have a toolbox, then you can compute those messages, and that's all you need to do. So with a toolbox, this becomes almost trivial. If you don't have a toolbox, you need to derive it, and then you have to do stuff like this. Yeah, that's it's possible, but you don't want to take this like even more complex than a regular Kalman filter, right? Kalman filters, technically, I mean, in the purest form, a Kalman filter is this. Let's say it's based on this generative model. So it's a model where the state transition is a Gaussian, Z of t, the linear combination of the previous state. Px of t is also Gaussian distributed depending on C of t, and you start off with your hidden state in the Gaussian. So that means that if the generative model is sort of the multiplication of all these Gaussians, and if I multiply Gaussians with Gaussians and Gaussians, and basically I'm going to get a one big Gaussian. So any inference problem in a linear, this is a linear combination, right? Linear combination. Any inference problem in a linear dynamical system with Gaussian noise will result in a Gaussian. And these messages, I mean, in a vector graph, they're quite easy in Gaussian networks. Any deviation from this model assumption is technically not like a Kalman filter. You can call it like, yeah, Kalman filter-esque, or we don't generalize Kalman filter because it's not a linear dynamical Gaussian system. And you might have non-linearities in there, and so you will probably don't have a Gaussian for your posterior. So there's all kinds of ideas also in the vector graph toolbox that you can do to approximate the posterior as a Gaussian, or you can linearize it. All kinds of ideas. Yes. Yeah. So if I write let's say the first equation here, so the question are A and C the matrices of the state space model? The first equation is nothing but saying Z of t, and this is a vector, right, is A times Z of t minus 1 plus some Gaussian noise, V of t, and V of t is distributed as a Gaussian sigma z. This is the model, this is the state space notation or state variable notation that people usually use in control theory. Right, and the observation is x of t is c, like some linear transformation of the states, plus noise, let's call it wt, and wt is distributed as a Gaussian zero mean sigma x. This model is a linear. Right, and then you start the whole thing off with Z1 is also a Gaussian. Well, what do I use? Mu1 and sigma 1. Good. So this is exactly the same model as this model. It's linear. You don't see any squares, any logarithms, right? It's just the output is a linear combination of inputs. The output is a linear combination of inputs. And the only uncertainty is in this system are V and W, and they are Gaussians. So it's a linear Gaussian system. Right? It's just that if we want to, let's say, use sum rule, product rule for Bayesian inference, it helps to write it in this way. This is the same system, but once you write it in this way, then you can ask yourself any task, any inference task, right? You can say, oh, I'm interested in Z of t given everything that I've seen until this point, and the evidence for x of t given the past. And then you just multiply it out, you get these factors, and at some point then you say, oh, I recognize this one, because for my likelihood, I use this Gaussian. For my state transition, I use this Gaussian. And this is just this thing, let's say, delayed or one time step earlier. So when we just define a Gaussian for that, and then we just proceed and find updates for U of t and sigma t. If you do it in this way, you can use the rules of the Gaussian multiplication rule, stuff integrating to 1, and you get an expression. I mean, you get an expression that posterior times evidence is, everything is equal, is, here's the evidence. This is a Gaussian, and this is the posterior with parameters ut, sigma t, and they're given by, you can compute them in this way. Note that this evidence, if x1 to t has been observed, is just a number. I can just put in, I can just I can put in this the value and just get a number. So this is a Kalman filter. Kalman filters are used almost everywhere, and also if this happens to be some logarithm and that or not Gaussian, it's still the same factor graph. It's just you get different messages. It would still be the same thing. So factor graph approach is not limited to linear Gaussian systems, right? In fact, I could say, well, maybe z of t is not distributed as a Gaussian, but maybe it has just discrete values, right? Maybe if observed values here are like the diameter of wheels, it helps to know if something is either a truck or a personal car. And that's just a binary, or like a discrete variable. So we call those systems hidden Markov models. That's the same graph, right? So in a hidden Markov model, the state variables are discrete valued. There's no other difference between Kalman filters and hidden Markov models. In most literatures, hidden Markov models is a completely different literature, and everything is different. So not in a Bayesian framework, right? You just have it. It's the same graph, it's the same structure of the network. It just, the only difference between a dynamical system and a hidden Markov model is, oh, is this z of t defined on the real axis, or is it discretely valued? There's no other difference. You can still pass messages, you can still do prediction, smoothing, everything. So that's why I don't do a derivation here. But the only difference, if I would do the derivation, is instead of Gaussians, I get categorical distributions to do summations, and you would recognize all the same formulas that we did in the classes before, right? And that would be filtering with hidden Markov models, and hidden Markov models before, let's say, the deep neural network era. So quite recently, until like 10 years ago, when deep neural nets started taking off, hidden Markov models was the model for stuff like speech recognition and that kind of thing. Because, well, we want to recognize words. Words are discrete things. You observe speech, which is a continuous signal, and you want to do inference. Right, you want to, let's say you observe a signal, speech signal, and you want to find which word was spoken. Maybe you have a vocabulary of 100 words. Well, it's an inference problem. And here, in the transition, you can take language model or language constructions into account, right? Like before let's say a noun, you might have a particle like the or an, or after a Q, you probably get a U. So the transition probabilities get into place there, right? That may also help you recognize what word is spoken or what letter was spoken. Yes?
So, in your example, you said the z of t will be the words, right? So, the discrete
Sure, yes, yeah.
X of p will it be continuous, or how would X of p change in Barkov models?
Well, the general idea is that you observe a speech signal, and it may not be exactly this model, but the general idea is that what you observe is going to depend on what word you are speaking, right? I mean, if a word like backward can be pronounced in an infinite number of ways, so you have an infinite number of possibilities of how you observe it, but the search space is extremely constrained by knowing that it's backward that you're saying. The speech recognition problem is, I make some observation of speaking, what word was responsible for that observation? And a little bit earlier, say here I have another string of signals. What word was responsible for that? What I for the string that I observe. So hidden Markov models were very popular, and all kinds of variants of hidden Markov models have been developed with, hierarchical hidden Markov models and all kinds of things. But generally, you could just draw them as vector graphs, and you can do inference in them. And that was what speech recognition was about until the internet age, and we had databases of a gazillion number of words, and we could just train models with 1 billion parameters, and that's deep learning, right? Yes?
Can we represent hidden Markov models using that number?
So the question is, can we also represent hidden Markov models this way? Yes. So in a hidden Markov model, the transition probability, usually we would just say, well, the probability that I go from, let's say, the case state to the J state is Aj of k. Right? Let's say I go from one particular word to another word. I just give each transition. They're only discrete transitions, right? And I give them all a particular probability. So this is the transition probability. It's just a categorical distribution. For each, let's say, observation that you have here, you have a categorical distributions over the next one. Okay, so it's about time. So are there any other questions about this class? I hope you recognize that I didn't really, dynamic systems is, you can have a whole semester or 2 semesters on dynamic systems, right? And there's a whole lot to say about it. And they're very important because most of what we observe in the world, and most of what we do in signal processing control, they're all time series, right? It's just that technically we didn't have to introduce anything new. There's nothing new. You just make a model assumption, and you do the inference that you are interested in on that model. And if you do that in a Bayesian setting, and then for particular model assumptions, you will retrieve all kinds of algorithms that are known in the literature, Kalman filters, hidden Markov models, and so forth. There's all kinds of algorithms that in a Bayesian setting, you don't really care what the name is. You just do inference, and the right algorithm rolls out. So that's the main message of dynamic systems. So don't think of them as something really special or really difficult, just apply the tools of some product rules, probabilistic modeling that we've done in the past, and everything should work out totally fine. Okay, then final question, and then we're going to take a break.
Can you go to the Kalman filter?
Can I go to the Kalman filter? Just here?
What is done in the mean transformation?
Yeah, so what we use in this derivation, I mean, you see a lot of times, you see, let's say, you see this, right? X is C of t, and I actually want to get Z of t here, but I don't want to get C of t here, I want to get C of t. You know, I can exchange these. And then I have C times Z of t given X of t and this. But I want to get Z of t here. And so it turns out, and you can just work it out for yourself, this happens to be this. It's exactly the same expression. It's just the same expression. And that means I can actually move Z or Z of t to here and in some way account for that, that multiplier here. Right? Because I moved Z here to here. It's just a generalization of moving the main argument and the mean, but now with a scaling factor. And we use that a lot in the derivation, and that's all that's going on. Okay, so let's then get back at 11:45, and then I will ask Wouter to give some overview of Bayesian kind of projects that we do, also a bit in industry. It's up to you. If you want, if you're totally not interested, then just go for lunch or whatever. But if you're interested, then come back, and then we'll see you at 11:45.
Nederland?